This is going to be a video over the study guide for Exam 1. Those of you who are in class on Friday, I've already seen a lot of this, but I'm going to go through the whole thing this time. Everything in yellow on this front page is going to be gone. So if it's not in yellow, it will be part of the front page. If it's not, it will be done. It will not be part of the front page. So these are the list of properties for the enumeration system, which you will get. The place value, base, uniqueness. You'll be listed, but you need to know what they are and how to use them. Place value, remember, is the fact that if a symbol is in a certain place, it can change its value. If symbols never change value, then they don't have place value. For instance, down here, the Egyptian symbol, this little hump right here, is always going to be 10, regardless of where you stick it. It never changes value. So the Egyptian system doesn't have place value. The Roman numeral system doesn't have place value either, because an I is always 1. A V is always 5. It doesn't matter where you put it, it's always going to retain the value of 5. Our Hindu-Arabic system does have place value because a 2 will have a different values depending on where you put the 2. For instance, if you have 2, whoops, why didn't that work? We have 2, 2, 2. Each of these 2's, although they look exactly the same, is going to have a different value based on its place value. This place it will be 1. This place it will be 2 20s, and 2 10s, and this place it will be 2 100s. So this is 200, 20, and 2. So where the value, even though the symbols are identical, the value stays the same. It changes depending on where it is located in place value. So that's place value. Egyptian doesn't have it. The Babylonian system does. Notice the only 2 symbols you have for the Babylonian system are the sideways V and the stick. And whether or not this sideways V means 5 or it means 5 times 60 will depend on where it's placed. Whether or not this sideways symbol means, what the heck, why is it doing that? Whether or not this sideways symbol means 1 or it means 160 will depend on where you put it. Again, let me give an example. For instance, if you have, this is the 1, I'm just going to draw a regular old 1, and then colon, and then you have the same thing repeated, and then colon, and then you have 1, and the same thing repeated again. Each of these will have different values. Remember your Babylonian system, this is your 1s, this is your 1s, this is your 60 raised to the 1, and this is your 60 raised to the 2. And this also brings up the base property. Your base has to be raised to a power or you don't have the base property. This is actually 60 to the 0. 1 is always anything raised to the 0th power. Okay, so here you're dealing with 1s. If you look back at the sheet, right here, this is a 1 and this is a 10. The sideways V is a 10. So what we're looking at is we're looking at 1, 1, and 10, and 10. Okay? Here we're looking at 160 plus 10 60s plus another 10 60s. Okay? So you're looking at one set of 1. You're looking at 1, a 10, and a 10. So this value is just 1, this value is just 10. When you go on this side of the colon, you're now on the 60th place value. Like, it would be the same as going from 1s to 10s. In the Babylonian system, you go from 1s to 60s. Think of a clock, minutes, seconds, everything's in base 60. Here you got 160, not just 1, 1. And here you have 10 60s and another 10 60s. So that's the difference here. Now, when you go up here, 60 squared is 6 times 6, which is 36. Add 2 zeros is 3600. So now you have 3600. Now, and then you have these. Now this stands for 2 3600s. I'm sorry, 10 3600s. Okay, so you have 3600 plus 36,000 plus another 36,000 would be your total here. So these 1s do not hold the same value. It depends on where they are in the place value system of the Babylonian number system. If you have place values, if the same exact symbol ends up looking the same. Okay, base property. Again, this is a good example of base property. If the same number is being multiplied or raised to a new power, starting with 0, 1, 2, etc., then you're dealing with base property. The Roman numeral system does not have base property because to talk about 1, it would be just 1 times, that could be anything to the 0, that works. But then 5 could be 5 to the 1, so you could say this is 1, this is 5 to the 1. But then 10 would have to be 5 to the 2, and it's not. 10 is 2 times 5. 50 is 10 times 5. So you're writing down multiples of 5, but you're not writing down powers of 5. You're not raising 5 to a power. So this is not a base system. Now the Egyptian system does, because this is 1, this is 10, this is 100, this is 1,000, and this is 10,000. So these are all powers of 10. This is 10 to the 0. This hump, which is 10, would be 10 to the 1. This is 10 to the second, 10 to the third, 10 to the fourth. So these do have base properties. This does have the property of base. So Babylonian has base 60, Egyptian has base 10 like us. The Mayan system has base 20. Okay, so this slash right here, this horizontal, would mean 5 when it's in the 1 place. Since it's in base 20, when it's in the base 20 place, it would mean 5 20s. This is going to be 1 in the 1 place, this little dot. When you have them in a new base, it will be 1 dot of 20. So once again, let me go ahead and go in here and show you what that looks like. So let's say you're looking in your Mayan system. You have dot, dot, slash, slash, and then here you go slash, slash, dot, dot again. Slash, slash, dot, dot again. Okay, you should only have one level of dots. That's how you know you're in a new base, is when your dots start repeating. Your slashes, you can only have if they're 5 each and this is base 20, you can never have more than 3. Because if you have 1, 2, 3, 4, 5, guess what? You've got 5, 10, 20, 5, 10, 15, 20. Well, this is base 20, so that's going to go up here to 1 dot. Okay? So these are equal to 1 dot because in the new base. So here I'm going to put a line there. There's my place value. So now you have 0 ones. So you draw your loaf of bread. And you have 1 set of 20, all right? So your first level is going to be your 1s, or your 20 to the 0s. Your second level is going to be your 20 to the 1 level, and your third level will be 20 cubed, and then it goes on from there. Okay, so once again, you see symbols repeating themselves. You see the 2 lines. These 2 lines stand for 5, 10, and these 2 1 stands for 1, 2, so that would be 12. Here you're in the 20 to the first, you're in the next place value up. So this is now 5 20s. So 5 times 20, 5 times 20, which is going to be 200. And these 2 dots each stand for 120 apiece. So that would be another 440. So you have 240 at this level. Now at the next level, you've got 20 squared. That looks like a cube, but that's supposed to be a squared. You've got 20 squared. And 20 squared is 400. So now you have 5 400s and another 5 400s. And then you have 1 set of 400 and another set of 400. Okay, so again, what these stand for depends on where they are. So this has place value and it also has base. So the Mayan system is base 20 and it does have a base property. Uniqueness property. Uniqueness property usually only occurs when you have a place value. Because if you don't have place value, what difference does it make how you write it? You can put this little hump here on the Egyptian number system anywhere and it's always going to mean 10. It doesn't matter where you stick it. It will always stand for 10. Same thing with this. This is always going to be 100 regardless of where you put it. So it's not going to be unique because you can never change these values. Systems that have place value are unique because if you move things around, you've just changed the value, since where they sit, where their place is, that was how you determine what their value is. Okay, most systems have the multiplicative and additive property. The 3 we've just looked at all did. How do I know you had the multiplicative? Because you have 10 here, and these are a value of 3,600, so it was 10 times 3,600, which is where I got the 36,000 for this value. These are each 10 sets of 60, which is going to be 10 times 60, 10 times 60, 1 times 60. Same thing with the Babylonian. You have 2 20s, which involves multiplication, 2 times 20, and then you have 5 20s and 5 20s, which involves multiplication. To get your final answer, you have to add all these values together. I mean, the answer for this would be 2 3600s plus 10 3600s plus 10 3600s, 10 36,000s, 10 36,000s, plus 60 plus 10 600 plus 600. You'd be adding all these together, okay? So these have the additive property as well. So does the Egyptian. I mean, you would this has the multiplicative property too. If I drew 2 of these humps, you wouldn't say that was 2. You would say that was 2 times 10. So you're using the multiplicative property for almost all number systems. Our Hindu-Arabic, if you have 2 in the hundreds place, that means 2 times 100. I can't think of any numbering system we have that wouldn't use the multiplicative property, to be honest. And then you have to use the additive property to add up all the different values you have to see what your final complete total answer is. So if you had 2, so yeah. Anyway, sorry. So this, again, you'd have to add all of these together to see what your final answer is. So almost everything has multiplicative and additive. The zero property, you either have it or you don't. I mean, you know you have it because you can see it. I see nothing in the Egyptian system that has a zero, so therefore it doesn't have the zero property. The Mayan system has a zero. So yes, it does have the zero property. Our number system has a zero. There is nothing that represents zero in the Roman numeral system, so that would not have a zero. The Babylonian system does not have zero. The Babylonian system does not have zero either, because if you remember, there was a problem. Let's say if you have something like this, where you have the colons, and then you have another colon, and then you have, let's say, something like that, okay? The fact that there's nothing between here means this would be the 60 place value, this is the 60 squared, and this is the ones. Okay, it means you have no 60s. But there's nothing in here to say you have none. There's no zero. It's just a blank. So it does connotate that it's empty, but there's a difference between something being empty and actually having a symbol that represents zero. And that's the difference between systems that have zero and that don't, is they actually have a symbol. So there's only two in all the stuff we did. That was the zero here for the Mayan, and our own Hindu-Arabic system has a zero. The rest of them don't. If there's no things there, they just leave it blank. Okay, you need to know your basic models or concepts, and these are going to mainly come up with the fraction problems more than anything else. Join, union is addition. I'm not going to list what these were. Like comparison, you need to know what that is. That would be one of the models for subtraction. Take away, subtraction, array, and array and repeated addition are multiplication. Combination is like permutations. It would be how many ways can you write DSL, SLD or something like that. That would be that. Combinations are more permutations, different arrangements of things. How many different arrangements can you get? Sharing, remember, or partitive is division. That's when you're breaking something into, how many groups, but you don't know how many is going in each group. So you're giving out pencils to 6 people, but the question is how many pencils is each person going to get? Repeated subtraction is where you're getting 5 pencils to everybody. The question is how many people or how many groups can get pencils if you give 5 away and you have 20. So you'd be able to give it to 4 groups. So that's when you know how many you're giving away, but you don't know how. You just keep subtracting till you run out and then find out how many groups you got. And then missing factor or inverse of multiplication would be division as well, and that's where this is kind of division and multiplication, where you can switch these to be, in either order. You can turn a division problem into multiplication and multiplication into division. Okay, this is the real number system. You guys seem pretty good at this. Your whole number system is the real numbers. Over here you've got irrational numbers that involve non-perfect square roots, your non-repeating decimals, and pi. You've got over here on this side, you've got your rational numbers, which is any number that can be repeated, can be written as a fraction. And remember, you can do that with decimals that don't repeat, that just truncate, they stop, or repeating decimals. So if decimal repeats, or it doesn't go on forever, then you can write it as a fraction. Integers, here you have your negative. I guess the good way to think about it is your negative and positive whole numbers. So it's basically both directions on the number line, only whole numbers. Then you've got your just basic whole numbers, which start with 0 and go on. And that's pretty much the only number systems I'm interested in. Things to know: 2A through C. Be able to write a repeating and truncated decimal as a fraction. For the homework, you'll need to be able to do problems like 2A through E this is actually session 1. Yeah, I'm in session 1. Where you write repeating and truncated decimals as fractions. Just to remind you what that looks like, that would be something like this, where this is a truncated fraction, so you just simply find out the place value of the last digit. 1 is in the tens, 4 is in the hundreds, 2 is in the thousands. So you have 3142 over 1,000. Don't write 3.142. Technically you can, but that's pointless, because you just write the whole number. You don't need decimals when you're talking about fractions. Remember, when you have a repeating part, I'm not going to give you any that have like a repeating and a non-repeating part, because that's too confusing. You can pull that off and ignore it and just add it back, just to show you what I'm talking about. Here's an example of a repeating decimal. Let's say you have x equals, whoops, I'm off the page here, x equals 3.142. All right. First thing, when you have anything that's a whole number, you're not interested in writing that as a fractional part, so you can just put it over here. So this is going to be 3 plus x equals 0.142, okay? And again, let me put the repeating symbol over the top of it. So you have to figure out how many decimal places you need to move the decimal to capture at least one repetition of the repeating part. If we move the decimal 3 places, we'll capture one repetition. So we're going to multiply by 1,000. So we're going to take 1,000 times x is going to be equal to 1,000 times this, which is 142.142142. All right, so there's your repeating part right there. All right, I guess you don't need to actually draw the repeating part over it, so let's just ignore that. Okay, so there's your 1,000, and then remember, you take the 1,000x and you subtract x, and our x is up there. Now the reason I'm writing it down here, and you're going to subtract it, you're only subtracting the fractional part. Okay, now the reason I wrote the 1,000 here, everyone's like, why did you repeat it? Because I can't take 1,000 from x. X is smaller. So I had to move the 3 down here. Now remember, there's going to be a 3 added on at the very end. That 3 I pulled off to ignore it for a minute. So you're taking 1,000x minus x, all right? That gives you 999x. Equals 142. This is all going to cross out, so you're just left with 142, which is the repeating part. Then you're going to divide that by 999, just like you would if you were solving any equation, and you end up with x equals 142 over 999. Then you're going to add this 3 back. All right, so your answer would have been 3 and 142.9 over 999. The 3 is a whole number. There's no reason to ever write a whole number as a fraction. So if there's a whole number attached to this, you're just going to ignore that part, because the only part you're interested in writing as a fraction is the decimal part, because decimals and fractions both stand for partial numbers. They're not whole numbers. So that, so anyway, this would have been your final answer when you're doing that. Okay, so don't forget how to do repeating decimals when you're doing this. All right, so that's what you need to be able. 5AD, this is on homework session 1. You should be able to answer these 4 questions and explain why. So let's see, what was 5AD? Does every fraction have a decimal representation? No, only repeating and truncated decimals that end and repeat. True or false? Adding 2 numbers always gives a sum larger than both numbers? No. Always remember, whenever you're asked for something, always check your negative numbers and check your fractions. Because usually when you add 2 numbers, you're going to get a bigger number if they're fractions or whole numbers, as long as they're positive. But remember, when you add 2 negatives, you get a bigger negative. And then finally, D, dividing 2 numbers always gives a quotient smaller than the dividend. That is not true if your numbers are less than 1. If you're dividing a fraction into a fraction, you actually get a number that's bigger, believe it or not. If you take if you take 2 and divide by 4, divide by a fourth. 2, here, let me write this out. It'll be easier to see. Okay, so if you take 2 and divide by a fourth, then what you're doing is you're taking 2, here's 2, and you're dividing it into fourths. Dividing it, and remember, when you do division of fractions, you're checking to see how many fourths are there in the whole thing. Well, if you break 2 into fourths, you have 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be equal 8, which is actually smaller. So when you divide by a fraction, particularly when you divide a number that's larger than 1 by a number that's smaller than 1, your answer is going to end up being bigger, because you're looking for how many of these small values are in this number. Whereas if you said, what is 2 divided by 1, it would just be 2, because you're seeing how many whole values is in 2. Well, you've got 1, 2, so you're going to have just that many. 2 divided by 2 is 1. The bigger whole numbers you're dividing by, the smaller the answers, because you're dividing by whole quantities. You're not cutting the whole quantities into smaller pieces and seeing how many of those values are in there. So be aware of the fact that if you divide by a fraction, you're going to get, and the number you're dividing by is smaller than the number that you're dividing into, then you're going to get more than you started with. All right? So that was what that one was talking about. Be able to draw an interpretive Venn diagram. This comes from the homework. Let's see. Oh, here it is. The homework right here. I'll go and make this big real quick so you can see it. Just be clear. This 23 over here stands for people that just had a computer only. The word only should be in there. If they had a computer and a cell phone, then that would be this 12 right here, and it would also be this. Because even though they had a DVD, that's irrelevant. You're not asking they had a cell phone and a computer and a DVD. You're being asked, did they have a computer and a cell phone? Everybody in the intersection right here of these two circles is going to have someone who has a computer and a cell phone. This 8 is for someone who had a computer, a cell phone, and a DVD. So where all three circles intersect would be what that would stand for. Now this 6 down here is going to be people that had a computer and a DVD but didn't have a cell phone, because these two circles of the computer and the DVD intersect, but it doesn't intersect with cell phone. Okay, so you need to know how to read these Venn diagrams and interpret them. If you're having trouble with that, you probably need to see me so we can figure out how you make sure you can read that correctly. Okay, and that was pretty much what you needed to know on session 1 homework. One more time, you need to know the categories of these particular numbers, the rational, irrational, real numbers and stuff, be able to identify them and explain why they're in the categories. Remember, all this is just like the homework on the test. You have to explain. You need to be able to write a repeating or a truncated decimal as a fraction. And you should be able to interpret a Venn diagram, and you should be able to know whether a number is going to get bigger or smaller, or some kind of a concept question by division or something.